Okay, this is another topic on atmosphere itself. This is called lapse rate and stability of the atmosphere. Atmospheric stability. That is the topic name. Okay, give some note. What you are learning, you should always keep some note. Write down atmospheric stability. That is the topic for now. Atmospheric stability we are learning. So what is atmospheric stability and lapse rate phenomena? Lapse rate, you have seen that lapse rate means your temperature variation with the altitude is called the lapse rate. Temperature variation with the altitude or height is called lapse rate. You must know that as you go at a higher altitude, temperature drops. Example, if you go at the rooftop, you don't understand. But if you go at the top of the mountain, hill area, temperature drops. Darjeeling temperature is much lower. Why? Because as you go at a higher altitude, pressure drops, and pressure drops will also reduce the temperature drop. Because the gas mixture, the air becoming lighter, and it cannot absorb sufficient heat. As it is becoming lighter, it cannot absorb sufficient quantity of heat, and so the temperature gets dropped. Could you understand why temperature drop? If you go at a higher altitude, pressure is dropped, the gas mixture is becoming lighter, so it cannot absorb sufficient heat, so temperature drops. So, but how far? Up to 11 km, that temperature drop is observed. Lagvag, around 11 km, there is no specific boundary. Up to 11 km is found the temperature constantly going down with height. After that, temperature increases. Okay. So then temperature increases from in the troposphere. Temperature range is from 15 degree to minus 56 degree. 15 to minus 56. That is temperature drop. After that, temperature is rise. Minus 56 to minus 2. So it is a rise. So that is happening in the stratosphere. Why this temperature is increasing? Because the ultraviolet radiation is exposed over there. Large amount of ultraviolet radiation is exposed. So ultraviolet is absorbed by ozone, and that's why ozone is rising the temperature in that region. So in the stratosphere, temperature is rising because of ultraviolet radiation, which is high energy radiation. And ultraviolet is getting converted to visible, it is converted to microwave. Obviously, so heat is generated. That's why light getting converted to heat, very simply, at that layer. So temperature is rising. As you go at a higher altitude, more and more exposure of ultraviolet, and so temperature is more and more. How much? Up to minus 2 only. After that, again in the mesosphere, temperature is dropping because there are neither any absorption of IR nor absorption of any UV. Why? Because gas mixture is practically absent. In the mesosphere, the air is so light, you cannot breathe. You cannot breathe even in the stratosphere. You can breathe only in the troposphere. Not only that, on the top of the mountain you cannot breathe. You have to carry the cylinder. So forget about stratosphere and mesosphere. You cannot even breathe in the troposphere at a high altitude. How far you can go? So you can breathe hardly a few, not even 1 kilometer. Isn't it? You cannot breathe. So that's why in the aeroplane also, the air pressure is maintained inside. Otherwise you will be uncomfortable. Cannot breathe. So this mesosphere, temperature drops again from minus 2 to minus 92 degrees centigrade. Minus 2 to minus 92. That is the temperature ranges in the mesosphere. So mesosphere temperature is so low because there are neither absorption of air nor absorption of UV. Then again temperature rising in the thermosphere, which is extended up to 500 km and above. So there temperature rising a lot. Why? Mainly due to solar flare. Solar flare, constantly the solar is bumping, huge amount of heat is radiated to the cosmos from the sun, and we are receiving a very small quantity, still we are getting burned. Okay, if it is not properly protected by our magnetic field, we could not exist here. Mainly 90% or 95% is protected by this magnetic field. Rest 5% maybe you are getting protection from this ozone layer. Ozone layer contribution may be 5%. Magnetic field contribution is 95%. That way you can think of. Okay. So these sort of different protecting things. One is your magnetic protection, another is your atmospheric protection, making us alive. So temperature variation understood. So whenever temperature drops with the height or temperature rises with the height, that phenomena you call lapse rate. And as we are discussing about, just a few minutes back we are discussing about the adiabatic process. So here let's take the example. The air is getting heated up. A portion of the air suppose got heated up, but the surrounding will not be heated up, because the circulation of this air, until unless there is a circulation, this heat is not dissipated. Why? Because air is a very poor conductor of heat, and the process happening in the air always adiabatic. So this lapse rate that we are measuring here will be calling adiabatic lapse rate. Is it clear? Lapse rate means temperature variation with the height, and it is always adiabatic because air is a very poor conductor of heat. So that's why if we combine the two, it is called adiabatic lapse rate. Now usually we don't use or consider the effect of moisture. If you don't take the effect of moisture, it is called dry adiabatic lapse rate. And if you consider the effect of moisture, it is called wet adiabatic lapse rate. They will be different. Dry adiabatic lapse rate theoretically can be calculated as per 100 meter rise 1 degree temperature drop. Is the language clear? Per 100 meter rise upward, temperature drop by 1 degree. Very easy to remember. Per 100 meter 1 degree, per kilometer 10 degree. Anybody can remember? No calculation, no formula. Per 100 meter 1 degree. Remember that. Okay. Temperature drop. So that is the lapse rate in the troposphere. Now, and whenever we are talking about lapse rate, we are concerning about troposphere only. When we are talking about lapse rate, we are concerned about only troposphere, because we are residing in the troposphere. We are not concerned about stratospheric lapse rate, etc. We are more interested about the tropospheric lapse rate. Achha. Next, come to the point. What is a lapse rate? Is written there. Just you read out. A lapse rate is defined as the rate of change in temperature observed while moving upward through the Earth's atmosphere. As I already told you, temperature rise as you go at a higher altitude, temperature drops. How much is the temperature drop? Per 100 meter 1 degree. Temperature drop. That is lapse rate. Now, tropospheric lapse rate is negative. Stratospheric lapse rate is positive. So there is a change that is called inversion. The very first inversion that happens at the tropopause. Tropopause means topmost layer of the troposphere. That is called tropopause. So temperature variation from first is going negative, backward, then forward. First fall, then rise temperature. So there is a change that is called inversion. So first inversion that is occurring at the tropopause. Then there is a second inversion happening at the stratopause. Then the third one in the mesopause. Understood now? Zigzag pattern. Zigzag, zigzag. First this. Zigzag pattern. So this is the abstract. This is the pattern, as I told you. So in the troposphere, temperature here 15 to minus 56. Here there is some sort of perpendicular line you can see. That is happening because temperature suddenly did not change. Up to certain region it will be constant. To make people understand, it is given in a perpendicular line. The temperature is not changing much in this region. After that again temperature is rising. Then there is some constant, because this region, you just think over, this dot line, it actually does not exist. This is our imaginary idea. Practically there cannot be some dotted line in the air, isn't it? So that we think over. So here just there slowly the change is happening, and after that the change will be observable change. Then this is the lap state negative, lap state positive, lap state negative, and lap state positive. Rate at which temperature decreases with height, units gradually, C per degree centigrade per kilometer. Sometimes Kelvin per kilometer.
So C per
C means centigrade and K for Kelvin. Stability of atmosphere. Atmospheric stability condition. Okay. So to understand the atmospheric stability condition, you have to understand two more things. One is the DALR, WALR, and ELR. DALR is dry adiabatic lap state, WALR wet adiabatic lap state, and ELR environmental lap state. Let's understand one by one. As I told you, the air is bad conductor, so that's why anything happening in the air is a adiabatic process. So in the dry condition, what adiabatic process that temperature variation is observed is called DALR, dry adiabatic lap state. If the moisture exists, then it will be called wet adiabatic lap state. DALR value I told you 1 degree per 100 meter. Drop minus 1 degree per 100 meter. That is temperature drop. But if moisture present, sufficient moisture present, temperature drop will not be that much high. It will be 0.6 per 100 meter. Instead of 1 degree, it will be 0.6 degree, means 40% drop, 40% change. Why it is so? You have to concentrate your attention, don't talk, otherwise you cannot understand. This is not written here. You have to listen to me. A moisture filled air parcel moving upward. So, whenever parcel is moving upward, just imagine it's a balloon without the rubber lining. You can imagine anything. Just imagine there is a balloon rising upward without the rubber lining. So, that air parcel is moving upward. It is called air parcel. Now, system surrounding heat exchange is not happening because adiabatic process. Okay, air is very bad conductor, so it is adiabatic. Now, inside you have moisture. Now we are considering there is moisture. So when it is rising, there will be expansion. Due to expansion, there will be cooling. Due to cooling, moisture will be cooled down into droplets. A latent heat will come out. That latent heat will raise the temperature of the parcel. So temperature was dropping, but it cannot drop that much because of this temperature heat release. Due to latent heat release. So temperature drop is less. It is instead of 1 degree, 0.6 degree per 100 meter. That is called WALR. Is it clear? DALR, WALR, sure? Anybody has any doubt? Achha. Then next one, DALR, WALR, there is another one called ELR. That is called environmental lap state. Environmental lap state is nothing, it is measured time to time, any place, any area, any height, altitude is measured instantaneously measured phenomena. It is a parameter, just measured parameter. Right now we measured it here, you get some value. You go at 100 meter height, you get some other value. So specifically the value you are measuring is the ELR. Environmental lap state. This is how the temperature is actually changing. That is measured value, not theoretical. Earlier what I told you, these are all theoretical. Now actual measured value with some instrument, it is called ELR. Now you have to compare the ELR and ALR. And what is ALR? What is ALR? Combination of DALR and WALR is called ALR. One is DALR, another is WALR. So in general we call it, combined together we call it ALR. Adiabatic lap state. This adiabatic lap state and environmental lap state you have to compare. Which one is higher? If the ELR is higher, there will be turbulence. If the ELR is lower than the ALR, then there will be no turbulence. No turbulence means atmosphere is very stagnant. No movement of air happening. This phenomenon is called atmospheric stability condition. ELR more than ALR, unstable air, circulation happening. ELR more than ALR, whenever ELR more than ALR, ELR you understood or not?
ELR understood, but
ALR is actually combination of DALR and WALR. Because we always cannot say two different parameters, take one parameter for simplicity. some moisture will be there, some moisture may not be there. So in general we call it ALR, which is theoretical value. Theoretical value will be in between 1 degree and 0.6 degree. Okay, somewhere. So that is our ALR, and ELR is measured value. If the ELR is more than ALR, circulation is happening, and if ELR is less than ELR, circulation is not happening. That is called atmospheric stability condition. ELR means environmental lapse rate, ALR is adiabatic lapse rate. Adiabatic lapse rate is theoretical, environmental lapse rate is practical, measured. If ELR is more, circulation will happen. If ELR is less compared to ALR, circulation does not occur. If circulation occurs, we call it a turbulent atmosphere. If circulation does not occur, we call it a stagnant atmosphere. Sometimes we find circulating atmosphere, sometimes we get stagnant atmosphere. Okay, if you then these phenomena together is called atmospheric stability conditions. ELR more than ALR and ELR less than ALR. These two, either third one can exist, that is ELR and ALR equal. It may happen. In that case, it is called this ELR and ALR. Whenever it is equal, it is it may sometimes happen. It is, but then also it will be stagnant. But just prior to circulation, you can think over that. It is also stagnant, but prior to circulation, very ready for the circulation. And when ALR is more, circulation starts. ELR is less, circulation stops. So air circulation, sometimes we cannot understand why air is not blowing. We are feeling very hot. थोड़ा हवा होना तो अच्छा होता. You feel like that, and sometimes we feel इतना strong क्यों हो रहा है, वो रुकना अच्छा होता है. So this is happening because of these two phenomena. One is ELR and another is ALR. Lapse rate condition, if it is adiabatic lapse, more than the adiabatic lapse rate, then circulation happens, and if it is less than the adiabatic lapse rate, then circulation does not happen. This is the key thing actually. Why circulation is happening, why storm is occurring.
Why should we consider the air as a bad conductor?
Don't consider it. Practically it is bad conductor. But that's why we need fan. Circulation kar. Okay, because radiation is not sufficient, conduction is not happening. That's why you are doing the convection. Why you are using convection? फैन क्यों चलाते हैं? कन्वेक्शन ना, क्यों कन्वेक्शन करते हैं? क्योंकि कंडक्शन नहीं होता है इसलिए. अगर कंडक्शन होता कन्वेक्शन की जरूरत क्यों पड़ता है? क्लियर? This, as I told you, in terms of language, now see in the picture form. This is the air parcel. Now it has become expanded. Some work has been done. Cooling happened. So water moisture can be condensed here in the form of liquid droplets. So moisture heat is released. So temperature drop is not that much. It is compensated to some extent.
Because of the
Latent heat release. So it is compensating the temperature drop to some extent, and WLR is lower than DLR. You can just go through. I will not read for you. You can read yourself. पढ़ना आता है. I will explain, but I will not read for you. That is very bad practice, huh? Whenever you give presentation, never read it. इसे देख के पढ़ो मत, क्योंकि सब लोग पढ़ सकते हैं, अनपढ़ कोई नहीं है. Anyone can read, so let them read, ठीक है? But whatever you want to say, you just say. Don't read it forever. That is the first knowledge of presentation. Never read the PowerPoint. And PowerPoint sometimes for different educational purpose, sometimes you are writing a bit more, and but if you are giving real presentation, there should be just bulleted only one line text. Here I am giving some more because so that you can read something more. This is education purpose. I am not giving presentation in a business. If I give presentation in a business sector, then there will be only one line, and you have to give elaborate a lot, and with a lot of diagrams and sort of pie chart diagram, bar chart diagram. But here you have to a bit subjective now. This subjective bit descriptive. That's why this language is there. Why adiabatic? That is explained here. Why air is adiabatic? That was your question. Why you consider the air is adiabatic first always? Air is circulation until and unless there is circulation, heat exchange is not happening much. Slight it may happen, but it is not happening much.
But sir, what about the air circle happening?
Acha, I can give you a very now. Right now, I triggered to me. I can explain your this question. Listen, everyone. Molecules are moving at random. So that is the nature. That is according to Brownian motion. The molecules are just knocking each other, and they are changing direction. So the molecules are taking lot of time for diffusion. In a restricted region, it is just going in random in different direction. But it cannot go translatory movement into a long way, because the always direction is getting changed. So that's why it is restricted in a region, and so heat cannot be dissipated much. It is restricted always within a boundary, within a small region.
But sir, molecules are so small, so how can it?
No, they are knocking each other in such a way. Every time they are changing their directions. Brownian motion, just remember the Brownian motion. You will understand what I am trying to say. This changing, and so it cannot go out. Acha, one good example. From the center of the sun to the surface of the sun, you know how much time required light to pass from the center of the sun to the surface of the sun. How much time? Why so long time? Light traveling in a so high speed. How much is the speed?
Because the density due to gravity is also very high. That's why
No, light is not affected by gravity. That is wrong idea, because gravity cannot affect the light.
So it can affect in case of gravitational lensing.
But light, how much will be affected? How much you think now? Practically, what is happening here? Photon. Light is also photon particle, na? Just like the Brownian motion, as we are discussing now, it is happening there also. Just like the sort of volleyball. Hand to hand, the volleyball is getting transferred. So you are just giving it to you, and you are giving it to him, and then he it to you. That way is going. But the goalpost is at the other end, reaching not reaching at the goalpost. That way it is moving, and so it taking a very long time practically to reach to the goalpost. That is outside. Goalpost in this case is outside, getting ejected. It's taking so much of long time because it is passing through lot of phases. First phase is this volleyball ground. Then there is a second phase. Okay, and there the very high energy gamma radiation is converted to ultraviolet and X-ray. That way it is getting changed. Okay, and knocking with the molecules and the photon, the interaction. Always this sort of interaction is happening, and is taking long time to come out.
So as you can say that the light will not affected by the gravity.
Affected, but not
as considered as a particle, as a photon particle, so will be affected.
it has no mass, no mass. Photon has no mass. There should be some mass. No mass required. GMM by R square. Formula is GMM by R square. What is M? 0 M. That's why not possible. Okay. There may be some, it may affect to some extent, but very minute. Ignorable. Acha, next, see, temperature change. You just read out. Dry adiabatic lab state, as I already discussed to you. Dry adiabatic lab state means we are not accepting any effect of moisture. That is called dry. So that value also I told you. Here the dry means unsaturated. Dry means unsaturated with water vapor. And wet means there's water vapor is quite high. Okay, at least near saturation. If not saturated, it is near saturation. Then it is called wet. And if it is unsaturated, it means very small quantity of moisture present, then we call dry adiabatic lapse rate. In that case, we call it dry adiabatic lapse rate. As I already discussed with the parcel, the same thing is written here. That moisture is getting, whenever moisture is there in the air parcel, as the expansion is going on, there is a cooling. Due to cooling, there is a moisture content formed into liquid droplets of water, and latent heat coming out, that is raising the temperature of the parcel. That thing is discussed. Okay, you can read out at your leisure. It is already there, given to you. So it is written here. See, the moist rate varies between about 4 and 5 centigrade per kilometer. So 0.6 I have taken an average, because it is varying from 0.4 to 0.9. So 0.6 taken as an approximate. Stability, Z versus T, that plot. Actual lapse rate or dry adiabatic lapse rate, if they are very close to same, that is called neutrally stable atmosphere. That is called neutrally stable. These two lines both are representing the lapse rate. One is ELR, other one is ALR. These ELR and ALR more or less superimposing. See here, isn't it superimposing? Almost superimposing. If it's superimposed, then you cannot see that. So that's why I kept it a bit separated. But actually they are superimposed. So if the situation arises, then you call it neutral atmosphere. Neutrally stable, but is still stable. Now stable atmosphere, this DLR, actual average, less negative than 10.
So ALR means actual lapse rate.
No, adiabatic lapse rate.
So
Actual means ELR. When it is more than, see, this language indicates here, when it is this is ELR. Actual means it is ELR, environmental lapse rate. And ELR is, adiabatic lapse rate is ALR. So DALR, this is DALR. So this is greater than 10, then it is unstable. Greater than 10 means it is more than the ALR. So in that case it is unstable. And less than 10, then it is stable. There will be no circulation. Moist adiabatic lapse rate is not constant. Average is taken as approximately 0.6, point drop away, 0.6, minus 0.6 degree centigrade per kilometer. Oh no, sorry, it is kilometer. That's why 6. 6 per kilometer. This is 10 per kilometer. Per kilometer. It is a 6 kilometer and it is a 10 kilometer centigrade per kilometer. This you are comparing. Important notes, saturated atmosphere. Just read out. There is another thing I remember here at this moment. Sometimes what happens, what is our idea? Temperature should drop at a higher altitude, but sometimes just opposite happens. That is called inversion situation, and it happens due to radiation. Sometimes it happens due to radiation. It's called radiation inversion. You understand radiative heat transfer. Heat transfer can be conduction, radiation and circulation. Okay. So this radiative heat transfer that occurs particularly in the winter season afternoon, suddenly will feel temperature drop near the ground when we are going back from college to home, and the afternoon after the sunset, in the winter sometimes we feel suddenly the chill atmosphere just after sunset. So why does it happen? Because that time the atmosphere is very much clear. There is no cloud in the sky. Winter atmosphere is normally very cloud free, isn't it? And cloud has a very important role. It is reflecting the heat back to the ground. If cloud is not there, the heat is directly going to the sky without any barricade. So it happens in the winter. So whatever heat is absorbed in daytime, after the sunset, heat is radiated back to the sky and is not getting returned. So suddenly it is getting chill. The ground is chill, but upper layer not that much chill. The ground is lower temperature, upper layer is higher temperature. Opposite phenomena. That is called inversion. So this inversion is occurring due to radiative heat transfer. That's what is radiation inversion. Some extra information I told you, which is not written. Everything is not written here. Not possible also. So stability and instability I have discussed. So conditional instability, all these things. Anyway, so these things are already discussed. So I tell you some more information apart from this. As I told you, what is that? Radiation inversion, radiative heat transfer, and when does it happen? Winter afternoon. Another phenomena occurs summer afternoon. Okay, normally 4 baje, 5 baje, before the sunset it happens, and that one was after the sunset. Now in the summer, just before sunset, at around 4-5 p.m. in the afternoon, what happens? Some air parcel which is not visible coming downward. It is sinking downward, just like some spaceship is landing. The air parcel actually landing downward, and the cold air breeze going outward. Cyclic fashion, it is going outward. That phenomenon happens. It is not visible because air is not visible. That's why it is not visible always. But it is experimentally can be. You can get it by experiment. So this is called subsidence immersion. There also the upper layer is moist, hot, and bottom layer is cold. Cold breeze is going outward from the bottom portion. So the bottom layer is colder and upper layer is heavier and denser and humid, hot, humid, dense air mass that is sinking downward. What is this called? Subsidence immersion. This is called anti-cyclone situation. Cyclone, you know cyclone? Cyclone. क्यों होता है cyclone? Why does it happen? Because very high pressure air coming to fill up the low pressure region. Low pressure region is called depression region. So to fill up the depression region, the high pressure air is moving with a very high velocity. But the air is a very stagnant mass. Air is a very stagnant mass. Because of inertia, whenever a moving air mass is knocking the stagnant air mass, it gives the speed. Okay, वो घूम जाता है. And once it starts moving, spiral and spiral and spiral, it go on moving like this, and then sucking the air inside it, because there is a lot of hole created inside at the center of this real pool. Air current, the real pool, it is collecting the air and dust and everything inside. That is called tornado. You know, in the air mass, there is always a gap. That is called eye of the tornado. But eye dropped. Air pressure is dropped a lot because all the mass is moving outward. Why? Because it is moving circular way. So there is a centrifugal force acting. Because of centrifugal force, all the particles, dust, as well as air molecules, all are moving outward, out of the circle. And so inside there is a pocket generator. That is tornado. So these are all cyclone. Tornado is a cyclone, hurricane, typhoon. Hurricane, typhoon, these are generated on the ocean. And this tornado on the land mass. No, after some time it loses its energy because this moving, then it will need energy, na? So it is.
Inertia is also there.
Inertia is there, but slowly it cannot go forever. slowly it is losing its energy, that's why it's slowly releasing. For example, you are throwing a ball, so why it is stopping sometimes? Due to friction. Here also there is a lot of friction with the air in the surrounding, losing energy, and slowly it is losing its all of its energy and then getting dissipated. Okay. Acha, what is weather and climate? Acha, anti-cyclone could you follow? Those who are very busy with your discussion, personal discussions. Huh? Would you understand what is subsidence inversion? No. सुना ही नहीं तो क्या समझो? बातें करने लग गया कुछ लोग. वो लिखा नहीं है, मिलेगा नहीं दोबारा. Instead of listening here, if you again listen the video, that will also take time, na? Why not? Don't you learn now? That is the best. अच्छा, weather and climate. Weather is an instantaneous phenomenon. आज का weather कैसा है? Whether it is rainy day today or whether it is a sunny day today, that is the weather. And climate, over a period of time, maybe at least 10 years, data calculated, and the climatic condition of a particular area is declared. The climatic condition of this Kerala is like this, climatic condition of our West Bengal is like this. Total state, what is the climatic condition over a period of time on an average basis? That is climate. And weather is a very random data. Today's data, tomorrow's data. That is a data. That is a data only. Today's data, tomorrow's data. It is a instantaneous data. But all these data manipulated together, forming a complete model. I think this language you understand better. All this data you take, make it a complete model throughout the year. That is your climate.